Hello dear viewers, I am your friend Shadab Imam and currently we are dealing with the topic of queuing theory under operations research. And today we are going to see some examples on model 1, which is MM1 infinity infinity model. And to know more about this model, please visit the lecture number 89 where we have discussed this model in detail with various derivations and total analysis. So please watch the previous video, then come to this video. So let us move with the problem, and before jumping onto the problem, let us have a recap of the formulas which we are going to use in this MM1 infinity infinity model. So let us start with the first formula here. Probability that exactly n number of customers in the system. It is given by lambda by mu to the power n multiplied by p0. Now let us move to the next formula. Probability that no customer is in the system. So when it says no customer in the system, this means that the probability of having zero customer in the system, and it is given by 1 minus rho, and we can also represent this as 1 minus lambda by mu. Now let us move ahead. Probability that the server is busy, or it is also known as utilization factor. It is represented by a rho and it is given by lambda divided by mu. Now let us move ahead. So here we'll be calculating the probability of having n number of system where n is from capital N to infinity, and it is given by lambda by mu to the power capital N. Let us move ahead. Next is the average number of customers in the system. It is given by LS, which is also known as length of system. It is given by rho upon 1 minus rho. Now if we put rho equals to lambda by mu, we can find this equation in the form of lambda and mu. Now let us move ahead. Average number of customers in the queue. Average number of customers in the queue is represented by LQ. It is also known as length of queue. It is given by length of system LS minus of rho. Now let us move ahead. Average waiting time of customer in the system. So average waiting time in the system is given by WS, which is equal to LS, that is the length of system, divided by lambda. Let us move ahead. Average waiting time of the customer in the queue. So the average waiting time of customer in queue is given by WQ, and it is equal to LQ, which is the length of queue, divided by lambda. Next is the probability that the waiting time in the queue is greater than time t. So whenever we have asked about the probability of waiting time, we are going to use this formula. So it is given by lambda by mu multiplied by e to the power minus of mu minus lambda multiplied by time t. Now let us move further. Probability that the waiting time in the system is greater than time t. So now it has been asked the probability of waiting time in the system, and it is given by e to the power minus of mu minus lambda multiplied by t. And if it has asked the probability of waiting time in the queue, we are going to multiply here by lambda by mu. So I hope this is clear now. Now let us move ahead with the problem. So this is our first problem. Customers arrive at a first class ticket counter of a theatre at a rate of 12 per hour. There is one clerk serving the customers at a rate of 30 per hour. What is the probability that there is no customer at the counter? Second is, what is the probability that there are more than 2 customers at the counter? Third is, what is the probability that there is no customer waiting to be served? And finally, what is the probability that a customer is being served and nobody is waiting? So let us quickly solve this. And we have been given arrival rate lambda, which is 12 per hour. and a service rate mu which is 30 per hour. Now let us solve the first part here, part A. It has been asked what is the probability that there is no customer at the counter. So when we say no customer at the counter, we will be calculating P0 here. So P0 is probability of having 0% in the system, and it is given by 1 minus rho, or we can say 1 minus lambda by mu. So let us put it in the equation, 1 minus 12 by 30, and it is given as 0.6, or we can say 60%. So there is 60% probability that no customer is in the system. Now let us move to part B here, and part B says that what is the probability that there are more than two customers at the counter. So we already know the formula. Probability that there are more than two customers in the counter is probability of having n greater than equal to 3. Now why we have put here 3? Because the probability we need to find is to have more than two customers. Now if we see the formula, the probability of having n customers, where n is from capital N to infinity. So if we put 2 here, then we will include the probability of having two customers. But here it has been asked the probability that there are more than two customers. That means either there are three customers or 4, 5, that means more than 3. So here what we will do is we will take this capital N equals to 3. It is given by lambda by mu to the power capital N. And now let us put this value in the equation, 12 by 30 to the power 3, and it is coming as 0.064, or we can say 6.4%. So the probability that there are more than two customers in the counter is 6.4%. Now let us move ahead and let us see the third part. What is the probability that there is no customer waiting to be served? Now when it is saying that there is no customer waiting to be served, that only possible in two conditions. First is when there is zero customer in the system, so it is represented by P0, and the next is when there is one person in the system, so that one person is taking service and nobody is waiting in the queue to get the service. So the probability that there is no customer waiting to be served is given by the sum of the probabilities of having 0% in the system and 1% in the system. So let us have this, and 1 minus lambda by mu is the probability given by P0, and this is lambda by mu multiplied by 1 minus lambda by mu. It is given as probability of having one person in the system. So let us put the values of lambda and mu, and it is coming as this, and if we solve this, we will finally get the value as 0.84, or we can say 84%. So there is 84% probability that there is no customer waiting to be served. Now let us move on to the last part. What is the probability that a customer is being served and nobody is waiting? So when a customer is served in a single server system, only one customer can be served and there is nobody waiting, that means there is no queue. So the only probability here exists is the probability of having one person in the system, and this one person is taking service. So probability of having one person in the system is given by lambda by mu multiplied by 1 minus lambda by mu. Let us put the value of lambda and mu here, and it is coming as 0.24, or we can say 24%. So 24% is the probability that a customer is being served and nobody is waiting. Now let us move on and see one more question. It is very important question, so please listen carefully. Arrival rate of telephone calls at a booth are according to Poisson's distribution, with an average time of 9 minutes between two consecutive arrivals. The length of telephone calls is assumed to be exponentially distributed with mean 3 minutes. Now, determine the probability that a person arriving at the booth will have to wait. Second is find the average queue length that is formed from time to time. Third is the telephone company will install a second booth when convinced that an arrival would expect to wait at least 4 minutes for the phone. Find the increase in the flow rate of the arrival which will justify a second booth. And the next is what is the probability that an arrival will have to wait for more than 10 minutes before the phone is free. And finally, what is the probability that he will have to wait for more than 10 minutes before the phone is available and call is also complete. So let us start solving, and in this problem we have been given the arrival rate, or we can say we have been given the arrival time here, inter arrival time as 9 minutes. So the arrival rate can be given as 1 by 9, which is equal to 0.11 customers per minute, because the time here is given in minutes, so this will be 0.11 customers per minute. And the service time is given as 3 minutes. So the service rate is 1 by 3, which is equal to 0.33 customers per minute. Now let us move to the first part here. So let us see what has been asked. Determine the probability that a person arriving at the booth will have to wait. Now a person has to wait when the booth is busy. So that means we need to find out that the amount of time when the server is busy, and it is also known as utilization factor, and it is represented by rho. So rho is given as lambda by mu. So let us put the value of lambda and mu here, and it is coming as 0.33, or we can say 33.33%. So the probability that the person coming will have to wait is 33.33%. Now let us move to the second part, part B, and it has been asked that find the average queue length that is formed from time to time. Now we need to find here the average queue length, which is given by LQ, and we know that LQ is equal to LS, that is length of system, minus rho. Now if you put rho equals to lambda by mu in the equation of LS, and here we will get this particular equation. Now we will put the arrival rate lambda equal to 0.11 and mu equal to 0.33 in this equation. So let us do this, and from here we can find out that the length of queue is coming as 0.166 customers. And it says that the telephone company will install a second booth when convinced that an arrival would expect to wait at least 4 minutes for the phone. Find the increase in flow rate of the arrival which will justify the second booth. So we need to find the new arrival rate here, for which the person has to wait for at least 4 minutes. Now to install the second booth, WQ1 be at least 4 minutes. So the waiting time in the queue should be at least 4 minutes. So let's lambda 1 is the new arrival rate when WQ1, that is the waiting time in the queue, is equal to 4 minutes. So to satisfy this condition, to install the second booth, we will assume that the waiting time in queue is equal to 4 minutes, and according to this we will find out the value of lambda 1, that is the new arrival rate. So let us see the formula for waiting time in the queue. So it is given as WQ1, which is equal to LQ1 by lambda 1. Now one may think that we have already calculated the length of queue in the previous part, so we can put that value here, but it will be incorrect because there are two inputs in the problem. First is the arrival rate, second is the service rate. And if any one of them changes, the value of LS, LQ, WS, WQ, that means length of system, length of queue, waiting time in the system and waiting time in the queue, all the values will change. So once we can understand that here lambda 1 is going to be different, then obviously the value of LQ1 will be different from the one we have calculated previously. That's why I have put the subscript 1 here. So the waiting time here is WQ1 and the length of queue here is LQ1 for the new arrival rate lambda 1. Now what we'll do is we'll convert this LQ1 in terms of lambda 1 and Q. So this is the formula. Now as the service rate did not change, we will use the same notation here, which is equal to mu, and the service rate is equal to 0.33, which we are using previously. Now let us put these values in the equation. So WQ1 is 4 and this is lambda 1 we need to calculate. This is 0.33 mu and this is again lambda 1. Now from this equation we'll calculate lambda 1 as 0.19 customers per minute. So we have found the new arrival rate here, for which the waiting time in the queue will be 4 minutes. But actually what we need to find is the increase in the flow rate of the arrival. So this is the new arrival rate, but to find the increase in flow rate we need to find the difference here. So this is the new arrival rate and this is the previous arrival rate, and the difference between them is the increase in the arrival rate. So this is 0.19 and lambda is 0.11, so the difference here is 0.08, and this is the increase in flow rate of arrival. So it is equal to 0.08 customers per minute. Now let us move on to the next part. What is the probability that an arrival will have to wait for more than 10 minutes before the phone is free? So we need to calculate here the probability of an arrival when the waiting time in the queue is greater than 10 minutes. And this is the formula we have seen. Whenever it has been asked to find the probability of waiting time greater than time t, then we'll use this formula. Otherwise, if it has asked the waiting time, then we will use the formula for ws and wq. So please understand the difference. Here it has been asked what is the probability that an arrival will have to wait. So here it has been asking the probability, so we will use this equation. So let us put the value of lambda and mu and time t here. So time t is 10 minutes and let us see, it is coming as 0.036, or we can say 3.6%. So 3.6% is the probability that an arrival will have to wait for more than 10 minutes before the phone is free. Now let us move to the next part. What is the probability that he will have to wait for more than 10 minutes before the phone is available and the call is also complete? So the probability that waiting time in the system is greater than 10 minutes is given by this formula, and let us put the value of mu and lambda here, and the final value is coming as 0.111, or we can say 11.1%. So 11.1% is the probability that the waiting time in the system is greater than 10 minutes. So I hope this lecture is useful to you. Please like, subscribe and share. Have a nice day. Thank you.